Hi, I'd like to show you how to set up an equilibrium expression given an equilibrium equation. So here's my generic equilibrium expression. I'm going to put my products on the top and my reactants on the bottom. And I'm going to set that equal to my equilibrium constant, which is K. For my balanced equilibrium equation, I have little a to the big A, or little a to A, little b and B, little c and C, little d and D, where the little letters, the lowercase letters, are the balancing numbers, the coefficients for a balanced chemical equation. You can see that I have c to the c power, so my little c becomes my exponent in my equilibrium expression, d to the lowercase d, all over a to the lowercase a and b over b to the lowercase b. Again, reactants are on the left, products are on the right. They become products over reactants on a equilibrium expression. The substances that go into your equilibrium expression are gases and items that are aqueous. These are allowed to go in the expression. What isn't allowed would be a solid or a liquid. So for example, if D were to be a solid, that's going to get crossed off as far as the expression goes, and that would no longer be in my expression right here. So now that we know how to do an equilibrium expression, let's go ahead and set one up and then plug some numbers in so we can calculate an equilibrium constant. So you might be given an equilibrium equation, something like this, where we have three items, and we know it's equilibrium because we have the double-sided arrow. The first thing you're going to want to do is to go ahead and write down your equilibrium expression. Again, I need to put my products right here. These two are my products, and over my reactants, and that's right there. So all of these have coefficient 1s. They're imaginary. We don't need to draw the 1s out. So my power, my exponents on all of these substances will be a superscript 1. Even though we don't need that, it's a good idea to get in that habit because I think you're more likely to catch the exponent when it needs to be there if you get in the habit of always including your exponents. PCl5 will go on the bottom. And that's also to the first power. Now that we have our expression set up, all we have to do is substitute values in place of my placeholders, my variables basically. So for my concentration of PCl3, the brackets mean concentration. I could also put in a pressure, and that's okay. So I just go ahead and use square brackets every time. Again, more so just to set up a routine of always doing the same way to increase my chances of success. And then chlorine, which is 3.8 times 10 to the negative fourth atmosphere, so that's a pressure of a gas. And then in my bottom, 1.8 times 10 to the negative second. And again, just matching up my substances appropriately. If I go ahead and solve that in my calculator, I'm going to get a number that sounds something like 1.2 times 10 to the negative third. I'm going to box that so it's easy to find. Another problem that's slightly more involved but goes through the basic same steps would be this one, where I'm taking 1.9 grams of calcium sulfate and I'm dissolving it to make 2 liters of solution. So I'm going to go ahead and write down my equilibrium expression here. KEQ equals, but this time I see that I have a solid, so that's not allowed to be in my expression, whereas in the previous problem they were all gases, they could all be there. But this being aqueous and this being aqueous can both go in my expression. Now my coefficients on all of these are 1s. So again, my powers are just going to be the coefficient in front of the substance, which is a 1. The power here will be the coefficient in front of the sulfate, right there, which is also a 1. And that's all going to go over the calcium sulfate, which can't be there, so I'm just going to put a 1 as a placeholder. Again, the 1 doesn't really matter, just like these superscript exponent 1s, but it's a good habit just to always do that fraction so you do your setups correctly and you get that routine to increase your success. I know that I have 1.9 grams of calcium sulfate, it's all going to dissolve. So I can use this information in order to calculate my molarity of my calcium sulfate and also my molarity of calcium ions and molarity of sulfate ions. To start though, going to go with my 1.9 grams of calcium sulfate. I'm going to get that to moles. Moles is the goals for just about everything we do. And I'm going to put grams on the bottom of calcium sulfate, and I'm going to get to moles of calcium sulfate. Time you stack moles with grams, it's going to be 1 mole. And if you get the molar mass in grams of the calcium sulfate, 40.08, sulfur is 3206, oxygen 16 times 4, it ends up equaling right about 136. Now, if you keep all those extra decimal places, it's a little bit more than that. But for this tutorial's sake, we're just going to truncate that number down to 136. That gets me to moles of calcium sulfate, but I want to know molarity because molarity is what we plug into these substances. Well, big M, molarity is equal to moles per liter. So I need to have liters in the denominator of this problem. I have 2 liters given to me, and I'm just going to fill this top box with a 1 just so it's filled up. Moles per liter is what I'm solving for. If I go ahead and calculate that, I get the number 0.00698, and that's big M of calcium sulfate. Now, calcium sulfate doesn't appear in my expression, but calcium and sulfate ions do. So I'm going to have to convert this over into calcium ions or sulfate ions. And to do that, again, I need my balanced chemical equation and the mole ratios that are established from the coefficients. Now I have a 1-to-1 ratio. So if I have 1 mole of calcium sulfate, I have 1 mole of calcium ions. What happens is the calcium sulfate crosses off, the moles cross off, leaving me with 0.00698 times 1 divided by 1, so the same number, big M of calcium. Let me just move my camera over here. So this is my concentration of calcium, and since I have a 1-to-1 mole ratio of calcium and sulfate, it's also my concentration of sulfate. So finishing up here, I can go ahead and take my equilibrium expression that I have right here, and I can sub in my values I just calculated, 0.00698 times 0.00698, which is really just 0.00698 squared, all divided by 1, and that's going to give me a calculated value of 4.9 times 10 to the negative fifth. Hope that helps you set up equilibrium expressions from an equilibrium equation, and then go ahead and solve math problems in order to find the equilibrium constant. Good luck, and I hope you watch another one of my videos.